So good morning to all. So today we are here to discuss about the case of classical ideal gas by considering as a microcanonical ensemble case. Okay. So in a classical ideal gas we are treating, as we know, when we consider there is n degree of freedom, so there is n number of particles, so which have, we know that, which have 3 n degree of freedom when you consider in three-dimensional particle. So let me consider that n equal to 1 for a monoatomic case. So in that situation we'll have the three-dimensionally three cases will be there. So there will be associated degree of freedom will be 3 in that situation. So when you consider a classical ideal gas situation, so the volume associated with the classical ideal gas, we treat it as integral dq raised to 3n, okay, dq raised to 3n, and dp raised to 3n is the total volume of a classical ideal gas when you consider it into a situation in microcanonical ensemble. And now here we assume that two conditions, that is particle, the classical monoatomic particle, it's confined in a physical space volume, okay, that is confined in a volume V, so let me represent so. And also we said that the energy, the Hamiltonian corresponding to that, it will be lines between e raised to minus delta by 2, okay, e raised to minus delta by 2, okay, delta by 2, and e raised to plus delta by 2. Okay, so because we already discussed for a microcanonical ensemble, the total energy, the Hamiltonian corresponding to that, will be lying in between the e minus delta by 2 and e plus delta by 2. That means we also represented that it will be in this fashion, that is e minus delta by 2 less than HQP is the corresponding Hamiltonian, okay, and e plus delta by 2, okay. So within this region will be having the total energy corresponding to that. And also in this case, when you consider a classical ideal gas situation, we basically dealing with the different atoms, right? So in the ideal gas situation, so when you consider an ideal gas, so the particles within the ideal gas will be non-interacting particle, okay. So the particles are not interacting in ideal gas situation, and in that situation we can say that the potential energy will be equal to 0, because so we have a non-interacting particle here, particles in ideal gas, so the potential energy will 0. And when you consider the total energy, the Hamiltonian will be equal to what? It will be I equal to 1 to 3n, okay. So I equal to 1 equal to 3n, and which is equal into pi square by 2m, okay, where p is the momenta, okay, p is the momenta, and we know that pi square by m means it is actually representing the kinetic energy with respect to that, okay, pi square by 2m, okay. So we are only taking care of the kinetic energy, because the potential energy will be 0 because in ideal gas the particles are non-interacting particle. And now if I just consider only the position coordinate and taking the volume associated with that, so that I'll be taking only dq raised to 3n, okay. So the associated position coordinate, then when I consider that, the volume associated with the position will be v raised to n, okay, where n is the degree of the freedom corresponding to that, or n number of the n is the number of particle present in there. And now when you consider the total volume omega, the total volume omega of the, because we in the last class we have said that omega is a phase space volume, it is a volume of the phase space, that is a particular energy interval we are treating, okay. So in that case we can say that omega equal to v raised to n, because v raised to n integral d p3n, okay. So we'll be getting the total momentum space volume will be represented by the omega representation here. And also this volume we will be treating in between E minus delta by 2 less than or equal to HQP, okay, less than or equal to E plus delta by 2 area. Okay, so in this region we'll be actually treating the corresponding representation. And now if I say that V raised to n integral up to dp raised to 3n, so which Hamiltonian I already represent, and Hamiltonian is pi square by 2m here. So I can give this limit will be e raised to minus delta by 2 less than or equal to sigma I equal to 1 to 3n pi square by 2m less than or equal to E plus delta by 2 will be the corresponding representation we'll have. Okay. Now if I do so, I'll be having the corresponding volume of a momentum space I'll be getting from here. Okay. So in this fashion if I do, so dp raised to 3n, and since 2m is there on the either side, right? So if I want to represent in fashion of momentum, okay, that is I can represent this limit, that is E minus delta by 2. So this 2m I can cross multiply to 2 as here, that is 2m into E minus 2m into E minus delta by 2. Okay, now if I specify the limit between sigma I equal to 1 to 3n for a pi, that means I have to take the p root of this one, so that I'll be getting root of 2m e minus delta by 2 when you represent sigma I equal to 1 to 3 and pi, so which is less than or equal to what, this 2m has to be gone to this side as well, so we'll have root 2m e plus delta by 2. Okay, so this is the limit of that momentum space we will be getting for associated with the classical ideal gas. Okay, now if I represent the above condition, because we earlier we have represented a hypershell in this fashion in a momentum space where we have p on the y-axis and q on the x-axis, and if I do represent, so the hypershell, okay, so we have a hypershell, consider this as a treated as a circle. Okay, and we know that the energy limit of this part will be 2m e plus delta by 2 by this representation, from this representation. And also when you consider this one, it is root 2m e minus delta by 2, so that is a limit of or radius of this hypershell radius within that case. Okay, so we will be getting that. Now if I want to know the thickness between that, that is a, I'll be basically evaluating the interval, so difference between these two energy level. Okay, so this is a hypershell, basically a 3n dimensional space. Okay, so now I am just evaluating with this condition, so I am just evaluating the corresponding thickness of this hypershell, or rather I can say the interval associated with that. So that means if I measure the of the hypershell thickness of the hypershell, okay, so in order to find that, we have to take the difference between these two energy levels, that is root 2m e plus delta by 2 minus root 2m e minus delta by 2. Okay, so this is the corresponding representation we will be getting here, and which is equal to, so this is okay, so this is equal to, will, when you progress on the side, that is this I can represent 2me into, if I take e outside, that is 1 plus delta by 2e will be there. Okay, minus 2me 1 minus delta by 2e will be there. Okay, so this is how I will be getting. And now if I do represent the above representation in this fashion, that is root 2 me, I can take it outside because it is common in both cases. So root 2 me I can take it outside. Then 1 plus delta by 2e. Okay, raised to 1 by 2 will be there, minus 1 minus delta by 2e. Okay, raised to 1 by 2 will be there. Okay, this is I'll be getting. And further if you proceed this, we will get a, when you expand that 1 plus delta by 2e, we'll have 2 root 2 me into 1 plus delta by 4e. So I am just taking only few terms corresponding to that, and 1 plus delta by 4e will be there. Okay, when you expand 1 plus delta by 2e raised to 1 by 2. Okay, so this is a simple expansion of that. So if I do that, I will be getting 1 plus delta by 4e. So this is equal to, so that is equal to root 2me into 1 plus delta by 1 and 1 will get cancelled. Okay, so this 2 will get cancelled here. Then delta minus delta 4e minus, okay, this is okay, delta 4e plus delta 4e left. So that is we will be getting delta, okay, let me just write it, delta 4e plus delta by 4e will be there. So that is equal to root 2me into delta by 2e. Okay, delta by 2e is the corresponding representation. Okay, now I can reduce this one in further. So the thickness will be the thickness of hypershell. Okay, the thickness of the hypershell is equal to root 2 me. So this root me I can root e, and here e I can cancel, and root 2 and 2 also I can cancel. So I can represent this is equal to delta into m by 2e raised to 1 by 2. So this is the thickness of the hypershell we will be getting here in this fashion. Okay, so this is the thickness of the hypershell I will be getting, that is delta into m by 2e raised to 1 by 2. So this is the thickness of hypershell. Okay, now let me find out the volume of the hypershell here. Okay, volume of the hypershell. So here we considering basically the omega, that is dq raised to 3n dp raised to 3n. So that is actually the volume of what? Volume of the hypershell, or rather we can say that volume of the momentum space. Okay, momentum space. Okay, volume of the hypershell or momentum space. So how do we find? In order to find that, from the above figure we have shown, so we have to take the surface area. Okay, surface area of the hypershell. Okay, so hypersphere or hypershell. Okay, so hypersphere into thickness of the thickness in the momentum space, or thickness of the hypershell. Okay, thickness of the hypershell. Okay, so we just taking the volume of the hypershell, that, or volume of the momentum space, which is equal to surface area of the hypershell into thickness of the hypershell will be the corresponding value we'll be having. Okay, so for that, in order to find the surface area of a hypershell, we have a general equation that we call it as Sn. Okay, so Sn is a surface area of a hypershell. So surface area Sn is equal to, where n is actually representing the degree of freedom associated with that. Okay, so let me just mention Sn of r here, where r is the arc radius of the shell. Okay, so that is, which has the general equation 2 pi raised to n by 2. Okay, r raised to n minus 1 divided by n by 2 minus 1 raised minus 1 n by 2 minus 1 factorial. Okay, so this is a general equation corresponding to surface area of a hypershell, and here I am considering a 3n dimensional space. Okay, 3n dimensional space, that means n is equal to what? N is equal to 3n here, and the r is the radial vector or arc radius corresponding to that, which is equal to, I am just taking as root 2 me. Okay, now if I represent the surface area, so I can represent it like that: 3n of r s 3n of r is equal to 2 pi 3n by 2 r raised to 3n minus 1 divided by 3n by 2. Okay, it's capital N, right? So it is capital N. So let me just change it. So 3n, and here 3n by 2 minus 1 factorial. Okay, so this is how the surface area representation will look like. And also, if I do represent the it is in terms of r, I can substitute that r equal to root 2 me, like. Okay, so that is s3n of r, so that is equal to 2 pi 3n by 2, r I can substitute as root 2 me. Okay, so this I just represent that 2 me 3n minus 1 by 2. Okay, so this 1 by 2 is coming from the root of 2 me. Okay, from that representation I am just making a 3n minus 1 by 2 and 3n by 2 minus 1 factorial. Okay, hope you understand how this 1 by 2 came. That is from the root 2 me. Okay, that 1 by 2 I just taken outside. Now we know in this case, when you consider over a momentum space, okay, the volume of a momentum space, so that is actually we have to differentiate with respect to the momentum space. 3n is equal to surface area into thickness. Surface area into thickness, la. Surface area into thickness. Okay, so we already got the surface area, that is 2 pi 3n by 2 2me, okay, raised to 3n minus 1 divided by 2 divided by 3n by 2 minus 1 factorial into the thickness value. It is delta, that is already we identified. It is delta into m by 2e raised to 1 by 2. So this will be your volume of the momentum space you will be gonna get here. Okay, so this I just represented only in terms of dp, right? Okay, so the total volume means it will be equal to what? There will be a representation associated with the dq raised to 3n, and also there will be dp raised to 3n as well. Okay, so we already know that what is dq raised to 3n. So that is, we already mentioned that dq raised to 3n equal to v raised to n. Okay, now we'll substitute that into the above equation, so that we will be getting this is equal to v raised to n. Okay, so this is a second some part. So v raised to n 2 pi 3n by 2 2me raised to 3n minus 1 by 2 delta m by 2e raised to 1 by 2, let me just put a mark here, and divided by 3n by 2 minus 1 factorial. Okay, so this is how the whole representation will look like. And now the omega will be equal to, in this equal case, omega will be equal to v raised to n, v raised to n 2 pi 3 n by 2 2me raised to 3n by 2. Okay, so I can write 3n my 2me 3n minus 1 by 2. I can write it as 2me 3n by 2. Okay, into delta m by 2e raised to 1 by 2. Okay, so there was another one more minus 1 term was there, so this I can take into the denominator. Okay, so that there will be a term 2me in the denominator. What is 2me? If you take it out the numerator, you will be getting 2me raised to minus 1. Okay, so I can just simply sort it out like that, and 3n by 2 minus 1 factorial. Okay, so in this step what I have done is that this 2me 3n minus 1 by 2 I just split it out, 2me 3n by 2 and 2me raised to minus 1. So 2me raised to minus 1 means I can take that into the denominator. Okay, so I got this representation like in this fashion. Now we'll recall some earlier idea we having. Okay, so we already have been discussed about the case of what is gamma is. Gamma, we know that it is dou sigma by dou E. Dou sigma by dou E into delta. Okay, that means which was equal to, which already we have observed, 3n by 2 delta by E into epsilon nve. So this we have done in the first module section. Okay, and where sigma nve equal to what? It is equal to v by h cube raised to n, 2 pi me raised to 3n by 2 divided by 3n by 2 factorial. Okay, so these representations we already has been identified in our previous sessions. Okay, that is in the previous module we identified this representation. Now let me just introduce this value in the above value, that is sigma nve. I can substitute in for gamma. Okay, so I'll be getting gamma equal to what? If I do that, gamma I'll be getting gamma equal to, I'll have 3n by 2 delta by E, okay, into sigma. Sigma nve means it is a microstate as a constant energy level. So that is v by h cube raised to n 2 pi me raised to 3n by 2. Okay, 3n by 2 okay, and 3n by 2 will be there, and divided by, we know that 3n by 2 factorial, 3n by 2 factorial, I can split it out and I can write like this, that it is 3n by 2 into 3n by 2 minus 1 factorial. Okay, so which I can split like that, so the equation becomes, the gamma becomes in this fashion. Okay, so you just note down gamma corresponding to that. Okay, okay, so this is gamma here. And now what we need to find, we already identified the omega value here. Okay, so we already identified omega. Now we identified gamma. Okay, now we know that in the last class I have said about a volume, that is a fundamental volume. Okay, fundamental volume I have represented fundamental volume, that is a volume of a single microstate. Okay, fundamental volume is a volume of a single microstate, so that is equal to omega 0. So that is equal to gamma by omega, because we know the relation gamma equal to omega by omega 0. Okay, so this relation we have discussed in the last class. From that I will be getting omega 0 equal to gamma by omega. Now we already know that what is gamma is from the above representation. Now I can substitute omega 0 equal to v raised to n divided by h raised to 3n. Okay. Okay, sorry. Here it was to take, okay, omega 0 means it's not the equation, right? So, okay, sorry. So here the correction is, there's a correction. It is omega 0 equal to what? Omega 0 equal to gamma, omega by gamma, right? Okay, this is how the equation will come. Fundamental volume omega 0 equal to omega by gamma. Okay. Now, if omega we already know. What is omega? We already identified. Omega equal to v raised to n 2 pi 3 n by 2 2me. So this is the equation corresponding to the omega value. Okay. So this you take it out the downside, and also we got the gamma corresponding to that. Okay. So this is our gamma. Okay. Okay, we got gamma and omega. Now we can easily find it out what is omega 0. So omega 0 will be omega by gamma. Okay, so what is omega? That is v raised to n 2 into 2 pi me raised to 3n by 2. Okay, divided by 2me raised to 1 by 2. Okay. Okay, it was there. So would I represent in the earlier case like that? Okay, so it was 2me raised to 1 by 2 here. Okay, so omega, there is a correction, that is 2me raised to 1 by 2, because minus 1 by 2 will be there, right? So you have to represent it like that. Okay, sorry for that. Okay, so 2me raised to 1 by 2. So 3n by 2 and 3n by 2 we can so raised to 3n by 2 divided by 3n by 2 minus 1 factorial into the thickness value, that is delta m raised to half divided by 2e raised to 1 by 2. Okay, so we can represent that. And now this is omega, right? Divided by, we have to get the gamma value. What is gamma value? Gamma value is 3n by 2 delta by e. Okay, v raised to n by h raised to 3n 2 pi me raised to 3n by 2. Okay, so divided by 3n by 2 into 3n by 2 minus 1 factorial. Okay, so this 3n by 2 and this 3n by 2 get cancelled. So we can cancel these two here. And also when you do this division, we finally have to cut down this 2me 3n by 2, this 2 pi me 3n by 2 we can actually cancel. Okay, so these two get cancelled. Okay, so how do we represent this one? This is actually 2 pi, we can take it inside. Okay, pi we can take it inside, and we'll have 2 corresponding to that. And let me check it out. How do I represent the earlier one? Omega 2 pi. Okay, here you can see that omega 2 pi raised to 3n by 2 is there. So that I can take this pi 3n by 2 inside. Okay, so that's why this is 2 pi me. So that's why we are represented here 2 pi me raised to 3n by 2. Okay, So now we can cut down this one. Okay, we will cancel this one, and we can also cancel this one. Okay, and also we can cancel these two, get cancelled. And this 3n by 2 factorial, this one and this one got cancelled. Okay, and finally what do we exist? Okay, what do we exist is that when you solving this entire equation, what do we, the remaining is that we'll have omega 0 equal to, so what we finally will be getting that omega 0 equal to h raised to 3n is the only remaining portion will be existing after solving out these values. Okay, so the fundamental volume is equal to h raised to 3n, where 3n we know that it is the degree of freedom corresponding to that. Okay, so we have identified the total volume, and we also has been already has been identified the gamma corresponding to that. Now we identified the fundamental volume associated with the classical ideal gas. Okay, now if I say that let f be the degree of freedom, okay, degree of freedom of the classical ideal gas, then the fundamental volume will be, I can represent that, okay, h raised to f. Okay, so f will be the degree of freedom, then omega 0 I can just simply represent as omega 0 h raised to f, h raised to f. Okay, okay, h raised to f, so it is in the superscript. Okay, so this is how the case of classical ideal gas case. Okay, what we have done so far is that we just identified classical ideal gas treatment. We consider in by considering the total energy associated with the classical ideal gas, which lies between E minus delta by 2 and E plus delta by 2. So that is a Hamiltonian corresponding to that, and that Hamiltonian is only containing the kinetic energy term, because the particles in a classical ideal gas is non-interacting. So in that case the potential energy will be 0, and the total Hamiltonian will be only representing the kinetic energy associated with that. Okay, and from that kinetic energy representation we later on find it out the momentum space has a limitation which is in between, where so the hypershell have been limited from root 2 me e plus delta by 2 and root 2 me e minus delta by 2. Okay, then we try to identify from that momentum space the thickness of hypershell we identify by taking the difference of two energy levels corresponding to that. Okay, that is what we have done, and then after that we have to identify the total volume in the within, we have said that the total volume omega is representing the phase space volume, that is a that particular energy interval or in that particular thickness region. Okay, so in order to find that the volume of the momentum space or the volume of the hypershell, which is equal to what surface area of the hypersphere or hypershell into thickness of the hypershell. Okay, from that we identified omega value. Okay, and also from the last module session we already identified that gamma equal to dou sigma by dou E delta, where sigma is the microstated constant energy interval. Okay, from that representation we identified the gamma equal to, okay, so we already have equation corresponding to sigma and VE, so from that we identified what is gamma is. Okay, once you get the gamma, we studied in the last class the relation between fundamental volume and the volume of the momentum space, that is gamma equal to omega by omega 0. From that fundamental volume, the volume of a single microstate, that is equal to omega 0 equal to omega by gamma. Okay, so omega already we identified in this fashion, and gamma also we identified, and when you divide this like omega by gamma, then finally what exists is that omega 0 equal to h raised to 3n. Okay, almost all other term will be get cancelled, so that you can try out by yourself. Okay, if you try So almost all the term will get cancelled. The remaining only omega 0 equal to h raised to 3n. That is where h is what? H is the Planck's constant. Okay, where h is representing the Planck's constant. So h raised to 3n, where 3n is the degree of freedom for n dimensional structure. Okay, so when you represent, let f be the degree of freedom corresponding to that, then I can simply represent omega 0 equal to h raised to f. Okay, so that is omega 0 equal to h raised to f. That is the fundamental volume of a classical ideal gas. Okay, so that is what we have done today. So the fundamental volume of a classical ideal gas. Okay, that is the omega 0 equal to h raised to f. Okay, so that is about the discussion of classical ideal gas by treating as a microcanonical ensemble case. Okay, and then in the next class we will be discussing about harmonic oscillator. Okay, where we will be treating harmonic oscillator case by considering as a microcanonical ensemble. Okay, how do we the number of particle volume, then energy dependence will be in that case will be examined on the next section. Okay, so that's all about for today. Thank you.